the question that she asked
in chunk of change.
So, I'm Scott Allen Miller, and welcome to MangoCon 2019. This is our first session of the conference, and we're more of a meeting than a conference this year. So I'm opening up with NoSQL. So before I get started, how many people have actually worked with NoSQL in like production, like actually using it? Hey, that was a good idea. There he was. So to really understand NoSQL, we kind of have to back up a little bit and talk about databases as a more general thing, right? So just real quickly, what is a database? Right? Databases are a way of storing structured data, right? If we didn't have a database, we could easily just throw all of our data into a giant text file and just, look through it until we found what we needed. And that's not very practical. We want data that's structured in some way so that we can find things. So 1950s, 1960s, when computing was new, they started developing databases. They started off very, very basic, right? It may be very similar to a CSV today. Just enough that we could identify what data was, but the idea that we had to structure data is one of the fundamental concepts of computing. So databases are incredibly general as a concept, and we use them everywhere. We just don't often realize it because they're just built into things and they're underlying whatever. And in the late 1960s, early 1970s, the idea of relational databases started to emerge. With relational databases, which everyone is familiar with, we have very strong structure that goes way beyond something like a CSV, right? We have the concept of relations and integrity, potentially ACID. We have, atomicity. We have durability, all kinds of features, and we have highly regulated data types. So when making relational data, we may have a table that has, say, telephone numbers, and we have a very strict rule about what a telephone number looks like, and there's nothing in that table except for telephone numbers or very specific data types. And the database itself enforces a ton of rules to make sure that those things maintain their integrity, their commonality, and that's great. You're going to be looking through a whole bunch of phone numbers. The system's able to tune performance around that. It's able to tune data checking around that so that it's able to determine that what you have in there is good or potentially good. It can't tell if your data is actually good, but it knows that at least you're giving it viable data, right? Email addresses, right? Just anything. It has to be a number. It has to be text. Later, binary large objects are allowed in, and we're able to do a lot of things. It's very flexible. But fundamentally, we have lots and lots and lots of data integrity around relationships and stuff, so it becomes extremely structured. Over time, these systems became incredibly popular because all these reasons, right? They allow us to control data in very predictable ways. And because of that, we were able to build engines for them that were very performant. When you have a list of just telephone numbers, it's easy to make a database engine that can search through that at lightning speed, right? It just becomes very, very good at it. And we've had decades to tune these systems. Those systems, relational databases, have a tendency to be accessed through a common query language, which, developed by the person who also developed relational databases, is called the structured query language because it's structured data and you're querying it, which is known as SQL today. And because of the relationship between relational databases and the SQL language, over time, people have started to associate the term SQL with relational databases. They are associated correctly in that the two were developed together with the purpose of working together. However, they are two separate things. One is purely a query language that could query anything. You could query a CSV file using it, right? If you had an engine to do so. So it doesn't have to query a relational database. And a relational database can exist without access to a structured query language to talk to it, right? You could make one that talked through some other language. People don't because it's impractical, but you certainly could. They are two separate concepts. But over time, people began referring to relational databases, because it's a long word, who wants to say relational database, as a SQL database. Partially this came about because several leading database vendors use the name in their product. So Microsoft SQL Server is the most prominent, that they simply called it SQL Server, which is super confusing because it's like the 10th major production database that was relational, so calling it SQL Server was very confusing. MySQL has SQL in its name. Postgres while you don't hear it when you speak it, has the letters SQL written at the end of its name. So we tend to associate these things, although others like Informix or Oracle Database don't use the name. People just started using it as a nickname. So this creates a little bit of a misnomer. In 1998, a database actually named NoSQL was created. This database, and this is just a historical anomaly, but it's important to understand that these words don't mean what they say. The true NoSQL database made in 1998 was a relational database that didn't speak SQL. So it was truly the weird situation that I just mentioned where they were both doing what they needed to do and they didn't tie together. They just felt that a different language would be beneficial to that particular relational database. 10 years or so after that, there became a movement to start moving away from relational databases. At that time, some people coined the term NoSQL as a type of database to mean non-relational databases. They should have called it non-relational, not NoSQL, because it has nothing to do with the language you speak to, it has to do with the database underneath. So conceptually, this is a weird little thing that you just have to understand about these databases, that the term NoSQL has absolutely nothing to do with what they actually are. So stepping back, relational databases were created in the 1970s, but prior to that, we had databases. Many of them, right? They were a common thing. Everyone used databases all the time prior to relational databases. All through the time when relational databases were popular, and they certainly still are, right? They're still, all the leading databases are, well, at least like the top 4 are all relational. But through all this time, there were always alternatives. We always had other kinds of databases that we could turn to if we had different types of data. And I actually got my start in the field in 1989, building non-relational databases for Fortune 100, right? So this is actually my background, was not just using them, actually building non-relational databases. But so these were always there. So they've been there. They just weren't very popular, and we didn't have any major products that were built on them, or none that people knew about. Or ones that we used, but we used very little and just in the background, such as the Berkeley database, which people tend to be aware of. It's used in the background of products, but we never really deploy it, we don't run it, so people kind of forget about it. A lot of it is used under the hood in operating systems for other things, right? Some application will package a non-relational database all through the 80s, all through the 90s, and just not tell you about it because it just hides in the background. So they're there, but we weren't really aware of them, and we weren't thinking about them. And most importantly, they were being built and deployed by developers as part of other things almost exclusively. So as IT professionals, they didn't exist to us other than they were just, we had some files on a disk. What does that belong to? Oh, some database that you don't know. Okay. In the mid-2000s, there was this really strong move to say relational databases have kind of run their course. They're not advancing like they used to, and we have a lot of new use cases that are different than we had traditionally. So there may be an opportunity to rethink how we're structuring data on disk, and how we're accessing it, how we're querying it. So this really came about a lot, if people remember this term, Web 2.0. The big buzzword of 2005, right? Flickr and everybody with, oh, suddenly we have reactive websites and we want, fast reactions over a large geographic area with huge numbers of users. And we started getting use cases that didn't exist before. Because if we look at big use cases, for little things for databases are simple, right? It doesn't matter what you do. Those people who are making Access on their desktop, sure, Access databases might work on your desktop, but anything that's working for Access, you could have done in Excel. You could have done it in Notepad. It didn't matter, right? They may have been slower, but they would have worked. But when we start getting into big systems, say you're a Fortune 100 and you have financial systems, and you need to track the financials of hundreds of thousands of people and all the purchasing that they do and all the manufacturing of an IBM or something, right? You didn't just need a database that could hold all that information. You needed something that could move a lot of data really, really quickly because you were dealing with big numbers, right? So scaling up relational databases to make them big, the ones that were important, the ones that we got excited about as IT professionals, started being, we had to throw more CPUs at them, we had to throw more RAM at them, so we started building mainframe class systems, or mainframe near systems, mini computers, around database needs. And most of those things, if you're talking mainframe, if you're talking older, for those who remember IBM AS400 type stuff, those systems, the mini computers and the mainframes, basically existed to be databases. They didn't do too much else. You could run applications on them, but if you did, chances are it was a very light database front end, a very light application that was probably, green screen, text-based application, didn't use a lot of computing power, and a massive database that was doing all of the actual work on that platform. That's what those things were built around, and that's why they were built around high I/O requirements rather than high CPU requirements, like a lot of things are today. And it's why they were focused so heavily on durability, right? A single mainframe, often you could riddle it with machine gun fire and the thing would just keep on computing, right? They were concerned about data loss because that was pretty much the only thing it did. So even by the mid-2000s, if you wanted to have a really large database, if you had Microsoft SQL Server, right, and you wanted to go big, you were putting in 100 plus CPUs of Itaniums in a single chassis and terabytes of data. This is the 2000s, right? This is some time ago. These are giant systems. That's how you got your database big, because with relational data, there's no reasonable way to have it spread across multiple systems. If you have completely unrelated data, yes, you can have one kind of interface to it that's spread across multiple. There is sharding within relational databases, but it doesn't allow for a single data set that needs to be all queried together to exist in one place. So scaling up was a vertical scaling of simply throwing more hardware at it. It's how relational database works. And if you're an IBM, if you're a Fortune 100 company and you're dealing with financials, all of that really strict data integrity totally makes sense. The ability to build a mainframe or a giant mini computer with hundreds of processors in a single chassis, very doable. These were practical ways to deal with the problem. But with Web 2.0 in the early 2000s, we really started to deal with a completely different need to scale with structured data. And the big thing was that suddenly we had users. First of all, more users, right? We're dealing with users in the millions, not in the hundreds of thousands. There are very few companies outside of like military that are talking millions of people within a single organization. So internet websites very quickly were tackling problems that no one had really tackled previously. And they were tackling them in new ways. For example, people may be spread out all over the world rather than all in one place. And we were also not tackling challenges we had traditionally tackled in the past. Really giant databases within individual companies had a very high tendency to be focused on things like financials, HR records, production workflows, things that were really sensitive to any kind of anomaly in the data. So you start moving into web products, you start looking at the internet, most of the giant applications, whether it's Google, whether it's Flickr, whether it's your email systems, they're actually very insensitive to those things. They actually don't care. You can, let's say you're doing a Google search, if you don't get exactly the same results every time, you don't actually care. I mean, you might be a little bit like, oh, that would be nice if I got it, but it doesn't cause the product to break. Your customers aren't getting upset. Your customers probably don't even know, right? You can deliver data in completely different ways. It doesn't have to be 100% accurate because it's not calculating your taxes, right? So we started tackling new problems, but not having to tackle old ones. The needs of databases dramatically changed, and so the idea was traditional relational thinking that had gotten so much momentum in the 80s and 90s probably need to be rethought. And really, relational did a great job, but we really were dealing with it in an almost emotional way. And even today, there's a lot of companies, if you talk to them, they often approach databases in a, well, relational is enterprise and everything else is not, and they don't even know what other things are because we were taught relational in computer science programs and in IT classes. When you went through college and university and you took classes on data structure, relational wasn't taught as a option. It was taught as what databases were. And because of this approach, and not just universities, but this mindset was pretty much universal, most of us come from an era where IT simply believed that all databases had to be relational, and the question wasn't relational or non-relational, it was which relational products would we use. Are we going to use a big commercial one like Microsoft SQL Server or Oracle DB or IBM DB2, or could we use something smaller like Postgres or MariaDB or whatever? And of course, in the years since then, Postgres and MariaDB are now completely competitive with the SQL servers and the Oracle DBs, but that was how we approached it. So in the 2000s, we had to rethink all this and say, we need to step back and come back at this problem, looking at data from a computer science research perspective, and rethink data all over again. So luckily we had a lot of history of people in the background using other types of databases, but none of them were done in the same way. One of the big things about relational databases is that all of the ones that you know, with the possible exception of SQLite, if people are aware of SQLite, that is a glaring exception to the rule I'm about to state. But all relational databases that we know are not actually databases. We actually are familiar with the database management system that uses the database. Under the hood, there may be a different database that we're not thinking about, but we're aware of the management system. So the management systems you know, Microsoft SQL Server, Oracle Database, MySQL, MariaDB, Postgres. MySQL is a great example because it exposes its underlying engines, which are the actual databases. Its most popular today is InnoDB, but in the past, its most popular maybe 8 years ago was MyISAM. Several years before that, it was ISAM. There are several others you can get through it. Falcon, for example. You can plug in your own if you want. And so MySQL isn't actually the database. It's actually a management system of many different databases that each has its own identity and its own properties. And some of them are relational, and some of them are partially relational, and some of them are all kinds of weird things, right? But mostly, they're relational databases. That's why we think of it as a relational database system. Microsoft SQL Server, same thing. We think of SQL Server as a single relational database. It is actually a management system of several databases that don't have names anyone knows of, right? Microsoft doesn't say, hey, this is the such and such engine under the hood. They simply refer to it as the relational engine, the cache engine, the in-memory, whatever. But SQL Server is actually multiple databases under a single management overhead. But in those cases, MySQL, MariaDB, SQL Server, they all allow you to use the SQL query language, SQL, to talk to all of those products under the hood and present them as a single entity. So we think of it as a single database product, and many times we use it that way. Most of us who use MySQL, for example, are never going to access a secondary engine under the hood. We're just not going to, but we could if we wanted to. So it reacts that way. But other databases, right? All of the NoSQL that existed prior to this, none of them had the management system, or none that were large, but that is known at all. And so because of this, we perceive them differently. So in the mid-2000s, the big thing that happened was not just that we started rethinking data structures that were going on disk, but we started adding management systems on top of them so that we would perceive them the way that we traditionally perceive relational databases. And this was a really big step. Suddenly developers were presented with the same kinds of options, but they couldn't use structured query language because these weren't relational databases, and they just simply had the way that we ask questions in the SQL language were not going to give us the answers that we wanted. It didn't work that way because they were different. But other than having a different language, we now had databases that we could talk to and we could tie them into our applications. So the world started changing for developers and we got to start rethinking things. So what are these now? We have a background, right? So what I want to look at is a handful of popular NoSQL products today. So we actually have something tangible to talk about. But I also want to talk about, since relational is a very specific type of database, what are some of the most important non-relational databases? Because if we actually step back and look at the big picture of databases, right, it's not relational versus non-relational. It's not like that. Relational simply got so much momentum that we have to kind of make people step away and say it's not relational, it's something else, so rethink. It's kind of like if you come from the small business world, we think of it as there's Windows and then not Windows, right? But in reality, there's Windows, there's Mac, there's Linux, there's BSD, there's Solaris, there's AIX, right? There's all these separate operating systems. We just kind of lump them all into, do you know Windows or do you know something else? It's just kind of how we think about it. Relational's in that position. Over time, that will change, and people will stop having to refer to databases as non-relational before they get started. They can simply talk about what they are. But if you step back to the 1970s, we were talking about databases in a, well, there's a network database, there's a hierarchical database, there's a relational database, there's a key value database, right? They were all equal. They were all peers within the database world. We will eventually get back there. For now, we treat relational as kind of special because it just has too much momentum. So the most important of the NoSQL world is what's known as a key value store. Key value stores are pretty simple in how they work. They're actually kind of like a basic table. And I'm going to really oversimplify these things, right? So there's a lot that goes on under the hood. There's a lot of really amazing computer science that goes on to make these kinds of data stores really, really powerful. But the simplest is simply the key value store. And in a key value store, you have one basically column that has a unique identifier to a piece of data, and then another column that holds a piece of data. That's it. And that sounds really simple, and to use them is quite simple. The most important understanding of what makes something a key value store is that the data within them is considered opaque, meaning the database engine that talks to that database doesn't know what the data is. It knows to retrieve it, and it knows how to retrieve it, but what's in it is a black box to the database. So you can go to your database if you have a key value store and say, I need this ID of data, and the database will retrieve it for you. But it doesn't know what it's retrieving. It doesn't have any information about it. It doesn't, as it retrieves it, obviously it's reading it off of disk, but it doesn't know what it means. Key value databases are extremely dumb in this way, right? They simply don't have the logic to do these things. This also makes them really powerful. We can put anything in there, right? It's nearly unstructured. KVs are as unstructured as we can get while still being a database. And so it could be as simple as I have a key and I have a small text field that it's referring to. So with that, it becomes incredibly popular to use them in session data. If you're running large websites, you often want to have something that's storing session data in a really, really fast to retrieve way, often in memory, and key value stores are very popular to run completely in memory, but it's just a common thing to do. It doesn't mean that it's tied to that technology in any way. And so really simple data types like that can be retrieved very quickly and can be destroyed very quickly, key value stores are popular for that. The most popular key value store database out there with a management system, I have to say. So KVs are everywhere. They're actually incredibly popular. The GNU-DB, Berkeley DB, tons and tons of packaged, really small, really light. As you can imagine, with how little it does, you can have a really light engine for this. Have been traditionally bundled with software that developers will actually, build it in as a library. The big management system for key value store is Redis. And Redis, while it can be used for almost anything, is often used as a accelerator for session data. So if you're working with really large high-performance WordPress, for example, Redis is often used to accelerate that, places where Memcache can't keep up. Memcache is actually a key value store database as well, an even lesser one than Redis. So what's interesting, though, is that with the advent of products like Redis, and there's a lot, right? If you're looking at the key value store field, you have lots to choose from. But because we came in with these new management systems, right, we now have a query language for querying Redis. In the old world, we had to talk directly to the database and just code against it. But with Redis, we have a standard language. It's not SQL, but there's a standard language, and it's pretty easy to work with. So you can run a Redis server, put it somewhere in your cluster, and you can simply ask it questions. This is the data I need, and it retrieves the data for you. Right? So developers started being able to use it in lots of cases where they couldn't use key value stores before. And really quickly, to make Redis valuable, right, the Redis people started saying, the developers of Redis started saying, we need features that rival the traditional SQL servers and the traditional, relational database management systems. And so they started building the ability to cluster, right, and to have masters and slaves, and to have replication. And so Redis takes the key value store world and provides it in a, first of all, super high performance and very, very flexible to deploy so that you can build whole clusters of servers that may be 3 servers sitting in a data center. It could also be 10 servers spread out all over the world. You can make them replicate all the same data everywhere. You can make them only replicate certain types of data. You can have some that do only reads, some that do only writes. You can do all kinds of really powerful things because it doesn't have the strong relations that you're used to with a relational database system. The ability to replicate and cluster actually can get way better, right? because it just doesn't have all the complexity. So for a lot of really important data types, session data being absolutely perfect for them, this type of clustering really changed how we approach databases for simple data types. So KVs, very popular, and you will probably see them more and more, and a lot of us work with them already and don't realize it, Redis being the big one, right? A lot of people deploy Redis, not really sure what they're doing with it. A lot of times you have a product that says you're going to deploy Redis, and we just kind of do it blindly, right? And we're like, yeah, it's some kind of data product, but not really thinking about it. I was actually fortunate to be the head of Redis with change.org. So I had the Redis clusters were my purview. And it was a very interesting experiment, right? Large scale clustering of giant Redis systems. So we had, we were literally like 10 32 gig RAM Redis instances, all with high availability and automatic clustering. You can get into some really cool stuff that normally would be relegated to specific DBAs. But more and more in just the general IT field, we are seeing these products become available as something that we're realistically going to be deploying and managing. And so there's a lot of getting to understand them can be very valuable, right? In the late 1990s, if you said, oh, you're going to be working with MySQL and Postgres and SQL Server all the time, we didn't really work that way. In the late 90s, it was pretty much you had a DBA who worked on your SQL Server, and that was it. You had one big SQL Server, anything that needed it talked to it. And there was a specialist who worked on it. Most of us didn't deploy databases with any regularity. The early 2000s started to change that. At first, it was just the MySQLs kind of things that started coming around because we wanted them for like simple websites. But it didn't take very long, and it's hard for us actually today to remember that it wasn't that long ago that was the purview of a dedicated DBA. We wouldn't have touched those systems. But now we touch relational databases every day. I can't even tell you how many of them I run and how many of them do I even track, right? They're hidden within things, right? I just deploy them all the time and think nothing of it, and mostly they take care of themselves. And often the same thing is the case with NoSQL systems. If you're not using them in a dramatic way, if you're not really pushing them, if you're not doing clustering or high availability, you may be able to just ignore it. But it is important to understand that systems like Redis are like MariaDB or Postgres or Microsoft SQL Server. You can't just snapshot them just like Active Directory, right? And real quickly, Active Directory runs on a NoSQL database under the hood, right? And that's why you can't snapshot Active Directory without there being intelligence through the system, so that the cluster, the actual database cluster, needs to quiesce that data at a database level, not at an operating system level, not at a file system level. The database itself has to talk to its nodes, make sure it locks the nodes, gets the data into a quiesced state, gets that flushed to disk, then you can snapshot, right? So there's quite a bit of logic that has to go on when you have database clusters, even when they're a simple key value store, where that data may be out of sync or corrupt. And that's just a universal rule of database clustering. So it applies to everything. So key value stores are very simple to understand. The next type that I want to talk about, and that was Redis, for those, okay. So the next type is a document database. Now this sounds like it must be completely different than key value store, but it's actually not. A document database is often described as a non-opaque key value store, but by being non-opaque, it is a game changer and really, really gives us something powerful. So the idea behind a document database, and there's lots of them, it's a very common thing to be used, but there is one that is far and away the market leader and everyone thinks of when we talk about document databases. And is the only, this is worth noting, it is the only database that rivals the big four, Oracle and SQL Server and DB2 and MySQL in popularity. So document databases operate from a key value store perspective. They still have the identifying column and then they have the data column. So there's still just these two columns and that's it. It's still very simple. But unlike the key value store, where this was opaque and the database knew nothing about it, now this field, this data field, contains metadata that can be queried by the document engine. So what do we mean? So you may put in, let's just say you're going to be tracking something really simple, human resources records, right? We need to track the name, birth date, hire date, telephone number, address of people, right? Simple thing, we do it all the time. Relational databases, we know how that would work. There'd be a table for addresses, a table for phone numbers, a table for names, and then we'd have things that tie them all together. In a document database, we would probably approach this by literally putting into any given document, right? So you have one identifier that's just a universal identifier, UUID, and then you have your data field. In there, you'll have some kind of tagging. It may be XML tagging, because XML documents are not just a viable document format for this, but they're the most common to be used. It could be JSON or JSON, depending on how you pronounce it. I like JSON because it just looks like that. JSON is a really, really popular way of tagging things inside of a document database. Those two, far and away, are almost everything. But there are document databases that work with binary files, like encrypted Word documents, PDFs. These are viable document types for a document database, right? So when we say document, we mean document, right? Those are obviously much slower and much less common. Like, they're a very, very special case that you would build a database around that. But XML and JSON, YAML, things like that, very, very common. And you can obviously make your own that are flexible. But so you may use something like XML and simply say address field and put in an address. Telephone, put in the telephone, right? But because you have this metadata in a format that is expected by the database engine is able to open up an individual document and say, okay, we're looking at this one document, and pull all of the records out of it and know what they are. So you can, as a developer or as an IT pro, you can query the database and say, I need a phone number for this person. Find this person, query the database, find that person, find the document associated with them, pull out their phone number for me. You're not expected to use structured query language to do it, but a query language to do it, absolutely. So because of that, document databases move, even though they're still using the key value stored like concepts, they move us from this really, really abstract, how am I going to use that for anything complex world of like how Redis is going to work, to this really, really popular, you can just see how it could replace a relational database instantly, because you can query it in the same general way you could query a relational database. And some of the reasons that this is really powerful, and this takes a little bit to get used to really think about why this would be so much, I don't want to say better, but better for specific uses than a relational database. In a relational database, probably the most common thing for HR records, right? Let's talk about HR records because they're a great example. If you want to look up a person, and this is something an HR professional would do all the time. You want to look up a person, you got to pull their name, their address, their phone number, all that kind of data. In a relational database, that system has to go into table after table after table and assemble that data. And that takes time. That is complex for the database to do. Now, they're very good at it, and they have all these indexes to make it faster. But fundamentally, it has to assemble that data from a lot of different places and put it back together. And the normal use case is that you have to do that. It's not very common that you're going to go to addresses and look at all the addresses without looking at who they're for. You might. Definitely happens, and relational databases rock at that kind of query. I want to know how many people live in the 75000 zip code. It's going to tell you that's what it's built for, right? But I want to know everything about this person. Relational databases have to do a lot of work to do that. A document database is exactly the opposite. All of the information about that person is stored in a single document. So if you want to know all the details of that person, it's instant. It just finds the right document. It just has an index on whatever field matters to you, right? It's the same as relationals. You can build indexes on whatever you want. Can't index a key value store because the data is opaque, right? So it can't be indexed. You only have an identifier and an unknown bit of data. So it is what it is, right? The only thing you would ever query on is the universal identifier. But in document databases, you can be like, here's the phone number I need. Find me the person associated with them. Once you do, give me everything about that person. It's screaming fast for that. So for those types of use cases, which are probably the most common, document databases are very easily the highest performance type of database. Now that's just for retrieving data. But let's think about entering data. If you have to enter data into a relational database, and we'll use the HR example, you need to touch table after table after table to enter that data. When you do so, you have, under normal circumstances, you can turn these things off or find databases that don't have it. But under relational theory, you need to keep this data integrity in place. In order to do so, it needs to be able to update the user, the phone number, the address, the pay rate, the birth date, the hire date, all at the same time in all locations. It can't just happen once. It can't be pieced together. And so you need to lock a lot of pieces of that database in order to do so. And you have to touch a lot of places on disk or in memory. If it's in memory, it's pretty fast, but then it's got to get to disk at some point. So you're probably making a lot of disparate touches of things for simple changes. And a lot of different indexes need to be updated because there's new data for those tables. So writes tend to be extremely heavy with a lot of locking in the relational world. That's exactly what we want when we're talking about financial data. If we're tracking your taxes, if we're tracking your profits, we want everything to shut down and make sure the data is correct. Every time, no questions, every time, right? But if you're updating a human resources record and you want to have a person go in, well, you know what? If I can retrieve this in 10 nanoseconds, but they can't retrieve it for 300 milliseconds, that's okay, right? Because the person's either there or not there. If it's not there, we're okay with that, right? It's not like a tax record. We can miss it one time and just assume they weren't put in yet. That's cool. And we don't need to lock a whole bunch of different things. We need to lock one document. One single cell within our system is being locked at the moment that we're updating it. So unless you're querying that particular user, so when you're putting in the new, right, this doesn't really come up. It's when you're editing is when it really becomes a problem, that the relational is going to lock up an entire set of data in lots of different places while you're doing an edit. A document database is going to lock up just that one field just for a split second. So its ability to lock, its ability to read tend to be extremely, extremely good. And so the most popular document database that all of you should be familiar with at least a little bit is MongoDB. Mongo is somewhere in the 4th or 5th most popular database in the world at this point. Its rate of moving up the list is pretty incredible. And MangoCon runs on MongoDB. So some of the nice things about Mongo, some of the bad things, new licensing thing that just happened while we were preparing for this talk, they changed some of their licensing, so they're losing popularity pretty quickly because they have some pretty questionable licensing practices. But traditionally they've been open source. It is free. For those who saw the thread yesterday, I think it's been pulled out of Fedora because of licensing reasons. So if you want to get it, you have to deploy it on your own. It's not just bundled with operating systems anymore. It was 6 months ago. It's not anymore. But that's probably a good way to do it anyway because you want to control your versioning or whatever because it's a database. But MongoDB is insanely fast and it works on JSON. And one of the great things about it, and one of the reasons that it's really, really popular with developers today, I almost said modern developers, but it's not really true, it speaks native JavaScript across the board. So you query it using JavaScript, it returns JavaScript objects, JSON, it stores JavaScript objects. So if you're working in JavaScript, which pretty much everyone does at least sometimes, you can talk to MongoDB without a translation layer. You can serialize your objects, your prototypes within JavaScript straight into the database and pull them straight out. There's no translation. And so the ability to work with it with native tools is pretty unprecedented. And a lot of NoSQL databases are starting to look at JSON for that reason, because it's becoming kind of the lingua franca of those kinds of transactions. But Mongo really led the way here, at least in popularity, and it's very, very visible to the developing world, the developer world. That's a funny way to put it. That it works that way, right? So they tend to love MongoDB, and lots of frameworks choose to work with it. Meteor being one, right? It just integrates it into the framework, handles everything. With document databases like key value stores that they're based on, they have an ability to cluster that is really, really good. So building, whether it's a high availability cluster inside your own shop, or you want to build one that spans the globe, document databases make this possible for, as always, non-financial data. And even financial data, you can tune MongoDB and many other document databases to understand that they need to have ACID compliance, and they will simply lock up your cluster globally until they're able to replicate changes through it. You can do those things, but when you do that, you're taking an unbelievable performance hit. So if you have really specific use cases where you want to have NoSQL, you want to have documents, but you want really, really reliable data, those things are possible. They're just not what it's really designed around, and you'll probably want to choose another product for that. But not always. There are use cases for that. But for things like an online community, some of the ways to think about it, if we were doing relational data for MangoLossy or an online community, we would have one table that just lists our threads, and another table that lists our users, and another table that lists posts. And when you want to look at a thread, it's got to go look at the thread, see who the users are, figure out which posts are associated with that thread, and go through and assemble that thread. And those posts aren't in order, right? They're going to be all over the place. So it'll have an index, right? This isn't like crazy math. It'll have an index somewhere that it's able to put things together. Wow, that's odd. And by doing so, it'll assemble that data, but with a lot of work going on. And when you add a post to a thread, it's going to have to do the same thing. It's going to have to go update an index. It's going to have to make an additional lock in a couple different places to be able to put that data together. And a little bit over there, a little bit better. And that's very heavy. But if we did the same thing with a document database, we can have a document that is just a thread. And inside that document, it'll just have thread title, thread poster, right? Have the person, the ID of the person who did the post. And then all of the subsequent posts can be in a single document. So when we retrieve it, the database engine doesn't have to go looking all over the place for everything. It opens one document and goes, here's your thread. And it can do a lot to display it. It can manipulate it any way it wants. It can hide things, show things, have security. All those things can be in there. But its ability to retrieve it means the only index it needed was based on the thread title or whatever. It didn't need to have an advanced indexing. It didn't need to do a bunch of work to reassemble it because it stored it in the way it expected you to retrieve it. Now, if you want to retrieve all the posts by an individual person, you want to grab all of Jared's posts and you don't care what thread they were from.
You search for FFS.
Right, you search for FFS, that's the tag for Jared. And in a relational database, it would have no more effort to do that than it did for anything else because it's already doing this wild assembly in every situation. In a document database, this would be an edge case where we weren't expecting this query to come up very much. It would have to do a lot more work to go through and assemble those things and go into document after document and pull out the pieces that you wanted. Both situations can do the same work. It's just that one is tuned for one type of read and update and one is tuned for another. And so this is why it's worth really understanding how these databases work under the hood, because in real world situations, we may be in a position where we get to tune what we're using based on the expected use case. And there are situations, even in the pure IT world, where we're not writing any code, where we may be choosing between relational and non-relational databases. Some applications do give us those choices, and if we're working with bespoke software, we should be ones sitting with our developers to say, how exactly are you going to be using this data? How should we be looking at it from an IT and data storage perspective? Because a developer may only be looking at, well, this is the data I need to get somewhere. IT needs to look at what's our use cases really going to be, both from an end user perspective, and also how is IT going to be expected to make this highly available, fast, how are we going to take backups, right? And with all these things, right, backups are pretty basic. You always have to query the database for a backup, right? Doesn't matter if it's SQL Server, doesn't matter if it's MongoDB, doesn't matter if it's Redis. You're going to talk to the database and pull and have it take a backup for you because only the database knows how to talk to all of its nodes and get a consistent, full picture of the database. Because any given database, and this includes relationals, but in relational world, we're really used to any given instance of our database has the full database. So if you have SQL Server and you have a second SQL Server in a cluster, you can back up either one and you're going to get the whole thing because it's just how SQL Server does its replication. But if you have Redis, you have MongoDB, and you have 10 nodes, you take a backup of one of them, there's a risk you may have only gotten 1/10 of the data because that data may be all over the place. Okay, so, all right, so we covered document databases. Now, another type of database that generally grows just as documents extended key value stores, graph databases typically extend document databases. Now, this is worth noting, graph databases can be built on other things, and some popular graph databases are built on relational databases. So It's not an always kind of situation, but what makes graph databases unique is that they take existing database structures and add a new relationship model on top of them. Now, in some ways, they're a lot like relational databases because they have relations, but they're different types of relations. They're a more flexible and more powerful relationship type than you would get with a relational database, which is why they're often built on top of relations, and they'll use the relational engine to create the graph. But the more common way to do it is with documents, and the document database approach gives us a really easy way to kind of visualize what's going on with graph databases. If you were to take something like Mongo that we were discussing, you have these documents, they have information that's more or less what we would call object-based, right? You have a person, you have all the details about that person. You have a post and all the details about that post. That is a object in the developer world, right? We think of it as an object. And when doing that, we don't have any relations. We don't have any way to say, how does this object, how does this person relate to this team? A graph database builds relationships between objects, not between individual rows, the way that we're used to with relational databases. It takes these much more advanced, larger concepts and builds relationships between those. Relationships can be things like belongs to, is a member of, uses, right? So it's not a really difficult concept, but graph databases have so many moving parts and so many advanced features that often we think of them as very advanced databases. An open source one that has come up in the community. It is by far not the most popular graph database, but it is a really nice one, is dgraph. There was a whole thread. I don't think anyone here was the one asking. I have no idea who asked. They were talking about how to do reliable backups using dgraph. But it's open source, it's free. If you're interested in graph databases, that one is a good one. It's pretty easy to deploy. It has a lot of really advanced features. It's pretty new, so it's one of the reasons why it's not as popular. So all of those are database types that basically take key value store and then move it to new levels of advancement. The last type that I want to talk about, there's lots of different database types, right? There's a lot that we don't use anymore because they've just basically fallen away, or they're used in really specific cases. Like hierarchical databases still exist, but we never really run them as individual engines. The most popular one anywhere is the one beneath Active Directory. That's what it depends on. But if you use Active Directory through Samba, it does not use a hierarchical database. It uses a key value store, just how they implemented it. The last type, and this is possibly the most interesting, is called a wide column store. And wide column stores still use a kind of structure we would think of like a relational table, but it doesn't have the relationships between tables, so that's a pretty big difference. But what it also has is the ability for every row to define its columns separately. So this is weird, right? And it's worth looking back. When we looked at document databases, we said, a document has this metadata we can query. We can say, what's the name, what's the phone number within. But the schema for a document database, it doesn't require you to have the same schema from one document to the next. So you can change that. If you don't have a phone number for someone, you don't fill that in. In the relational world, we have to stay fully relational, we have to have these tables that connect things, and you simply don't record the phone number and it's missing in the phone number table. In a document database, you simply don't put that field into an individual document. So a document schema can vary from document to document. You probably want them to be similar for reasons of querying, but they don't have to be. They're not enforced because that's a relational concept. In wide column stores, you can have a different number of columns in every row. So the row is the master. A row has an identifier. A row then has columns within it, but from one row to another, you can have a different number of columns and different types of columns. Wide column is very popular to compete directly with relational databases in a lot of cases, and competes with document stores in a lot of cases. And in this case, I want to talk about two real-world databases that use this. One is Cassandra. It's made by the Apache project. Cassandra's claim to fame is just how enormous it can get. Wide column stores are probably the best for high performance, large scale clustering. So when you're talking people who want dozens or scores or possibly hundreds of database nodes, and you want to store things on an unbelievable scale, wide column stores are extremely good at this. The other one is it's a drop-in replacement for Cassandra. Cassandra is, I believe, implemented in Java and has a lot of threading challenges. Because it runs on Java, it takes time to spin up. And when you want to deploy it on a large scale, it's really designed around you deploying new nodes everywhere you're going to have it. So you want to have Cassandra get bigger, you're going to go on Amazon and you're going to deploy another 10 VMs, each one, relatively small and running Cassandra. Scylla decided to take compatibility with Cassandra and go in a completely different architectural way under the hood. And Scylla is really interesting for a couple reasons. One, because they're also open source and free, just like Cassandra. Two, they use a shared language with Cassandra, which is the Cassandra query language, right? So it's SQL, but with a C. But they really approach as if they're a relational database, but just slightly different. And they're actively a member of MangoCon in the community. So it's pretty cool. They're the one database company that you can go in and just talk to. They're on there every day posting. What Scylla does the exact same thing as Cassandra, but they write in C, so they don't have to worry about Java overhead. They had to do a lot more work to do it. They have a really aggressive threading engine. And so unlike Cassandra, which scales up simply by adding nodes, Scylla scales up by adding cores. So if you want to have 48 cores in a single database server, it's going to scale up to 48 times the performance it had at one core, right? Cassandra won't do that. You have to add more instances, or you have to run it in Docker or something to get around it, and that's going to have a lot of overhead and a lot of management. Scylla, just throw resources at it, it's going to keep scaling up. You can still have lots of nodes, but you can have lots of nodes with lots of CPUs on them. Wide column stores are often used more or less anywhere you would use relational data. And the way that they store, same kind of thing, if we had an HR record, we'd have a single row with an identifier and then a column that has really simple stuff, like here's a column for name, and it's one record for name. We're going to have a column for phone number, one record for phone number. It seems like it would be difficult to make this really work, but wide columns are super powerful for incredibly fast writes to disk, very fast retrieves, and very high ability to do compression. And so their ability to scale to really, really large and their ability to cluster over a large area is incredibly powerful because of the way that they store data. So wide column stores are often used in giant scenarios where just everything else has a lot of challenges. And so you will likely see them in really specific cases, but if you're deploying them, you're probably going to be spending a lot of time managing them. All right, so that's my overview. That's the 5 big products that I want you to kind of take away and say, if I want to look at something and play with something, you've got 5. All of those are free. All of those are widely available. You can go deploy them yourself, play with them in a single node, or build a cluster. Do some clustering. Once you see NoSQL, modern NoSQL products, it's not part of NoSQL, but in their clustering and in the management systems that come with them, they're doing a lot of advanced things that we're not used to seeing in the relational world. And so a lot of that's like really super cool. And one other that I just want to mention real quickly is Cockroach. It is a drop-in replacement for Postgres, and it uses SQL as its language, but it's NoSQL wide column store under the hood. And so it does amazing stuff with clustering, but performs completely different than Postgres. But because it's drop-in, you can compare them side by side. And when you deploy it, it gives you a web console with all kinds of information about its cluster, just built in. It's just part of the product. So it's really interesting. So that's some stuff to play with. Hopefully that gives you a good insight into kind of why other database types are important, which ones you should be looking at when, and how you can talk to your developers about them, and what you'll need to be looking at managing in the future. And that is the end of my session.